Haritha from IISER Bhopal, and she is going to speak on the alternative definition for the Parry's measure. Yeah, so we can start. Haritha.
Thank you so much. So good evening, everyone. First of all, let me thank the organizers for giving me this opportunity to talk. And my talk is basically about giving an alternate definition, a combinatorial definition for an interesting measure on a space called subshift of finite type. So this talk comes under the area of symbolic dynamics, which is a tool to model a large class of dynamical systems, such as expansive Markov maps and Anisov maps by a shift space. So to define a shift space, the ingredients required are a symbol set sigma, which can be finite or infinite, and a collection of infinite sequences with symbols from this symbol set. So let's define our setup formally. So we have a finite symbol set here, which is sigma, and then we consider the collection of all one-sided sequences, and F be a collection of words with symbols from sigma. So by a word, I mean a finite string. So a subshift is described by this collection F, which is defined as a collection of all sequences in sigma n where the words from F are forbidden, and it's denoted as sigma F. And there is a map on this space which is called the left shift map, and it is obtained as follows. So sigma of a sequence is given by deleting the first entry and shifting it to the left. So sigma is a finite set, it has the discrete topology, and sigma F is a subset of the product of this space sigma. Hence it has a product topology, which is a compact metric space with respect to this, and the map sigma is continuous. Let's see an example. So we have the symbol set sigma, which is 0, 1, 2, and the forbidden collection. So F will be called the forbidden collection because the words from F are forbidden in the subshift. And the forbidden collection here is 1. Then the subshift sigma F corresponds to all one-sided sequences with symbols from either 0 or 2. And this corresponds to the collection of ternary expansion of points in the standard middle third Cantor set in 0, 1. So one reason why this subshift is useful is that it has a simple representation in terms of a directed graph. So to get this representation, first thing that we need to have is this collection of forbidden words should be consisting of words of length 2. So first we start with collection of words of length p, then we'll see how we can get words of length 2. So when you have p is 2, there is nothing to do, and it's called the one-step shift. And when p is greater than 2, then sigma f is conjugate to a one-step shift, where the conjugacy is obtained by defining a new symbol set, sigma prime, which consisting of all words of length p minus 1, and the conjugacy is defined as follows. So conjugacy is basically a one-to-one correspondence between these two sequences. So we have sequence with symbols from sigma here, and that will go to sequence with symbols from sigma prime here, where the first symbol here is obtained by the first p minus 1 entry of this sequence, and then you slide it to the next position, and then you consider the next p minus 1 entry, and that will be the second symbol here, and so on. So now you can see a word of length p here will correspond to a word of length 2 here. Also, a letter, this letter is adjacent to the next letter only if the last p minus 2 entry of the first letter is same as the first p minus 2 entry of the second letter. So that's what is written here. Note that x and y, two symbols in sigma prime, then the word xy of length 2 is allowed only if the last p minus 2 entry of x is same as the first p minus 2 entry of y, which is called overlapping progressively, and then the word of length p obtained by joining these two words is not a forbidden word. So the new collection will have forbidden words of length 2. So once we have this conjugacy with one-step shift, we'll see how this directed graph is obtained. So for P is 2, you associate a directed graph where the vertex set is given by the symbol set and there is an edge from x to y if and only if the word xy is not forbidden. For P greater than 2, associate a directed graph which corresponds to the one-step shift conjugate to this subshift of finite type. So that means the vertex set will have all words of length p minus 1 and there is an edge from x to y if and only if they overlap progressively and this word of length p is not forbidden. So we have the directed graph now. So we can define the adjacency matrix to be there, to be a 0, 1 matrix indexed by vertices, and the xyth entry of this matrix is 1 if and only if there is an edge from x to y. Let's see an example. So we consider the empty set to be the forbidden collection. Then all possible collections are possible. It's allowed and it's called the full shift. And the corresponding directed graph is the complete graph with q vertices, and A has size q with all entries equal to 1. Then next example is with the symbol set 0, 1, and the forbidden collection here is this. Here P is 3, hence vertices will be indexed by all possible words of length 2, and the associated directed graph is given as this, and the adjacency matrix is this. So we have a space now and we have an association to a directed graph. So we'll use this to define a measure on this space, which is sigma invariant, where sigma is the shift map. For that, we need to assume that this subshift is aperiodic. That means the associated adjacency matrix A is aperiodic. That is, there exists an n such that A raised to n is positive. Once you have aperiodicity, then by Perron-Frobenius theorem, A has a largest positive real eigenvalue theta, which is called the Perron root, with positive left and right eigenvectors. And the topological entropy of sigma is given by ln of this Perron root. And entropy basically describes the randomness of the space and of the map, and there are two types of entropies. One is topological entropy, another one is measure theoretic entropy. In 1964, William Parry defined a sigma invariant measure, probability measure, which is now called the Parry measure, on an aperiodic subshift of finite type, which is unique and maximizes the measure theoretic entropy. What do I mean by maximizing the measure theoretic entropy? There is a variational principle on continuous map on a compact metric space, which tells us that the topological entropy is the supremum of the measure theoretic entropies, where the supremum is taken over all sigma invariant probability measures. And he proved that the measure that he defined is the unique measure where this supremum is attained. And the shift map sigma is ergodic and mixing with respect to this measure. Let's define it formally. So we have a finite collection of words of length p, and W be an allowed word of length n. We assume that it has length greater than or equal to the length of the forbidden words. It's a technical assumption. Then the cylinder based W is a subset of sigma f, which consisting of all the sequences that start with the word W. Then you define this Parry measure on this cylinder, which is U suffix the first p minus 1 entry of W times V suffix the last p minus 1 entry of W divided by theta raised to n minus v plus 1, where theta is the Perron root and U and V are the left and right Perron eigenvectors with U transpose V to be equal to 1. So, and this, you extend this definition to the sigma algebra generated by all possible cylinders. So we know that when you have forbidden collection with words of length p, then the adjacency matrix is indexed by all possible words of length p minus 1. So are for the left and right eigenvectors. And also it measure on a cylinder depends only on the first p minus 1 and the last p minus 1 entry of this word. And for the full shift, it's a uniform measure on all cylinders, and it's given by 1 by q raised to n, where q is the size of the symbol set. So our aim is to get an expression, combinatorial expression for this Perron root as well as the Perron eigenvalues, so that we can redefine the Perry measure. So we'll obtain an expression in terms of correlation polynomial, which is defined as follows. Let's say you start with two words of length P1 and P2, then the correlation polynomial is a polynomial with coefficients either 0 or 1, which is defined in the following way. You place W under U and shift it to the right by L digit. Then you look at the overlapping parts, and if they match, then BL plus 1 is 1, otherwise it's 0. Let's say, consider an example of U and W here. Then you place W under U, and then you look at the overlapping part, and you can see that they do not overlap, so B1 will be 0. Then you shift it to the left, shift it to the right and see if they overlap, and here they do not overlap. But when you shift it again, then you can see that this word overlaps with this word, and hence B3 will be 1, and so on. So this is, so what we'll have is, we'll write Perron root as well as the Perron eigenvectors in terms of correlation between the forbidden words. So we have the forbidden collection, and MZ is the correlation matrix, which is where ijth entry is the correlation between the words AJ and AI. And these are some terminologies. 1 by RZ is the sum of entries of inverse of M. Ri is the sum of entries of ith row of M, ith row of inverse of M, and Cj is the sum of entries of jth column of inverse of M. We'll see what these quantities are for the example that we already talked about. So we have alphabet size 2 and the forbidden collection given by 0, 0, 0 and 1, 0, 1. Then the correlation matrix is this, where you can see the first entry is the correlation of 0, 0, 0 with itself, and the other quantities are these rational functions. So all these quantities will always be rational. That is one thing. Then let's see how we can get Perron root and eigenvectors in terms of the correlation. So we assume that the forbidden collection has words of length P, and M is the correlation matrix. And AI tilde is a subword of AI obtained by removing the first letter of AI. Note that AI has length P, so you remove the first letter, so AI tilde will have length P minus 1. Then the theorem tells us that theta, the Perron root theta, is the largest positive real zero of Z minus Q plus 1 by RZ. And the vectors U and V defined as UX equal to this and Vx equal to this, where these things comes from the correlation between the forbidden words. For X of length P minus 1, then U and V are the left and right Perron eigenvectors of A. So now note that Perron eigenvectors are indexed by the words of length P minus 1, hence X is a word of length P minus 1. And it has an application to finding the Perron root and eigenvectors for any aperiodic 0-1 matrix, because any aperiodic 0-1 matrix will correspond to directed graph that will then correspond to a subshift of finite type. And now we have the Perron root as well as the Perron eigenvalues, but the only thing that is missing is we wanted the Perron eigenvalue to be normalized. So the next theorem gives the normalized form for the Perron eigenvalue, and hence the definition, an alternate definition for the Perry measure. So again, we start with an allowed word of length n, which starts with the P minus 1 word X and ends with the P minus 1 word Y. This is important because the Perry measure depends only on X and Y now. And the measure on this cylinder based at W is equal to this quantity, where you can see this was the left eigenvector that obtained before, and this was the right eigenvector obtained before. So what we proved that we normalized this eigenvector and hence got the Perry measure on the cylinders. And this new definition explicitly brings out the role of forbidden words in the subshift, which was not clear from the original definition. So in the original definition, the only thing that we knew was a word that start and ends with the same p minus 1 words will have the same measure. But now what we know is, let's say you start with cylinder based at two words with similar, with same correlation polynomials, then they both will have the same measure. So let's conclude by completing the example that we started with. So we have this forbidden convection. Then Perron root is the largest positive real zero of z minus 2 plus 1 by rz, and it's equal to 1.456, and Perron eigenvalues are given by these things. And then Parry measure, let's say you take w equal to 0.001, then the Parry measure is given by 0.1942. So these are the references, and thank you.
Thanks, Haritha. So we can take a few questions if anybody has.
Hello, Haritha, nice talk. I just wanted to know, you said something about the Q, I missed that. You know,
Sorry, what?
Q, there was a Q when you defined a matrix. A small q.
So Q is the symbol size of the symbol set.
Oh, okay.
Yeah.
Okay. I see. Because it suddenly changed from P to Q. So I'm confused.
Yeah. P is the length of the forbidden collection and Q is the size of the symbol set.
Okay. And is this work preprint or what?
Yeah. This is, it's on archive. So it's not published yet. So it will be available in this. Yeah.
Okay.
Thank you.
I have a question.
Yes.
Yeah, you said that you can have sigma as finite or countably infinite, right?
Yes.
But I doubt that you can do this for countable.
This cannot be done for, no. What I was doing is I was defining this shift space in general beginning. Then we looked at the subshift on finite alphabets, and this is true only for finite alphabets.
Yes, because the Perron-Frobenius theorem is not that easy for countable.
And Parry measure is also defined only for finite alphabets.
So is there any attempt to do this for countable?
I don't know. We haven't tried anything.
So the Perron-Frobenius theorem for countable metrics exists for recurrent matrices. And if from recurrent, I'm talking about the Markov shifts or the random box in that. So maybe this work can be done, extended to not every kind of shift, but those shifts who have the matrices which are recurrent, maybe.
Okay. Yeah.
Because I'm trying to do a similar work in Bratley diagrams. That's why
we haven't tried anything for infinite matrices. So sure, we can try that. Yeah.
Okay, so any other questions? If
one
not,
more.
let's,
Just
okay,
one more.
Yeah.
So is there some implication from graph theory? Can you go back and forth with
so that's what I said here.
Once you said that, so
when you have a directed graph, then you can always find the forbidden words because you can look at the edges which are not possible. So that will be the forbidden collection. So there is an associated subshift for any directed graph given. So in fact, this can be applied to any aperiodic 0-1 matrices because that has a directed graph associated to it.
Thank you.
Thank you.
Yeah, if there is no question, let's thank Haritha. Yeah, thank you very much.